Hi, my name is Shahnaz. In this lecture, we'll prove that there is no retraction of the closure unit disk onto the unit circle. But before that, we'll start with the definition of a retraction. So we have this definition. Let us consider a topological space. Um, and suppose A be a subset of X. A continuous map, say R from X into A is said to be a retraction of X onto A. If the restricted map R when restricted over A, so this is a map from A into A is the identity map. That is this restriction map is same as the identity map on A. And let us give an example of a retraction. So S1 is the retractor of the punctured plane R2 minus 0. So in this space S1 is the retract of the punctured plane. That is the space R2 minus the point 0. So one can note that. So since S1 consists all the pointers x, y, and R2 such that x square plus y square is 1. So this is of course a subset of R2 minus 0. So now for this set S1 we have the map uh, we have the map R from the space R2 minus 0 into S1 defined as this R takes the odd pair, just takes the point xy to the point x over square root of x square plus y square and y over square root of x square plus y square. So one can note that this point, I mean the length of the vector given by the point this over here has is 1, I mean. So note that the length of the vector rxy, which is same as the length of this vector over here, I mean the point x over square root of x square plus y square, y over square root of x square plus y square. So actually this is 1 because this is equal to the square root of, this is equal to the square root of x square over x square plus y square plus y square over x square plus y square. So this is 1. So this map is a well-defined map. So hence R is a well-defined map. So moreover, the map R rested over S1, which is a map from S1 to S1, is the identity map, because if I take, since if I take the point, since for say for z in S1 we have z is same as z by norm z, because norm z is 1. This is same as r of z. So hence this serves as the identity map. So it's same as id of z. So since for z and z we have this thing over here. So hence this is zero traction. So this shows that S1 is a retract of the ball B2. Sorry, the puncture blank R2 minus 0. Now we have a short lemma. So suppose A is a retract of X. So let A be a retract of the space X. So then the homomorphism, then the homomorphism of fundamental groups induced by the inclusion map, by the inclusion map, say I from A to X is injective. So this is a nice result. So we have the proof. So let us suppose, so let I a x from a to x be the inclusion map, be the inclusion map, and r from x to a be a retract. So be the retraction. Now one can note both the maps are continuous. So they induce the homomorphism of the corresponding fundamental groups. So since both the maps I and R are continuous, uh, we have the following induced homomorphism of fundamental groups. So we have the following homomorphisms of the fundamental groups. So now I from a to x is continuous. So this I will induce a homomorphism, say I star from the fundamental group of A based at suppose some point x naught to the fundamental group of x based at I of x naught, but I is a inclusion map, so I of x naught is same as x naught, and R star will be a map from the fundamental group of x, say based at the point, suppose suppose based at the point x naught to the fundamental group of x based at R of x naught. So we had to prove that this induced homomorphism is injective. So we wish to prove the map I star is injective because this lemma says here the homomorphism induced by the inclusion is injective. So that is we have to prove I star is injective. Now one can note that, so since uh, I is continuous, R is continuous, so is there. So one can note here. So since I and R are continuous, so is the composition R composition I, which is a map from A to A. So one can note here we have the map, we have a subset A here, uh, we have the space x here, and then we have the subset a here. So this is the map I here, the inclusion map, and this is the map R here. Now the fundamental group being the functor, so this takes this set A to pi 1 A based at the point x naught to pi 1 of x based at x naught. So this is the functor pi 1. So finally, so this is the group pi 1 A R of x naught. So this map I is carried out to the map I star. So pi 1 of I is I star. Similarly, pi 1 of R is R star. Now we have this map over here. This is the composition map. It is called, this is the map R composite I. So this map is carried out to the map uh, R composite I star, which is same as pi 1 of R composite I, because pi 1 is actually the functor. So what we wrote about, so R composite I from A to A is actually continuous, so this will induce, so so it is not just continuous, it is actually more than the continuous map. So it's actually uh, the identity map. So our composite I is continuous, and uh, the identity map, that is our composite I is actually the identity map on A. So hence the homomorphism R composite I star. So this will be a trivial map. So hence R composite I star is the trivial homomorphism. So this is actually a map. So this is actually a map from the fundamental group of A based at x naught to the fundamental group of A based at R of x naught. So this is the trivial homomorphism, and hence injective, because trivial homomorphisms are bijective. But pi 1 being a functor, so but pi 1 being a functor between the category of topological spaces and the category of groups, it preserves the composition, i.e., uh, pi 1 of R composite I has to be the map R star composite I star, but is the same as, or R composite I star is the map R star composite I star. But so let us bijective here. So but this map is bijective. This shows that I star is injective and R star is surjective. But we do not have to do anything with the subjectivity of R star. But this shows that the map I star is injective. So this proves the map I star is injective. Now let us prove a theorem. This is also called the no-retraction theorem. It says that uh, there is no retraction of B2 onto S1. Let us prove this. So we have, so B2 is the set of all pointers. Is a set of all vectors in R2 whose length is either less or equal to 1, and S1 is a set of all pointers in R2 whose length is precisely 1. So we had to prove there is no retraction of B2 onto S1. So assume on contrary that S1 is a retraction of B2. So assume on contrary that B2 is a retraction of, I mean, S1 is a retraction of B2. So this is the case, and let I from S1 to B2 be the inclusion map. So this B2 is this region over here. This is B2, and this boundary over here, this is the S1. So clearly we have this inclusion map, but we just proved that the induced homomorphism of this uh, injective map is actually of this inclusion map is injective. So therefore the induced map uh, I star from the fundamental group of um, S1 based at point B naught to the fundamental group of B2 based at B naught, where B naught is a point in S1. So this is injective. Now one can note that the fundamental group of the circle is the group of integers, whereas the fundamental group of the closed unit disk is just the trivial group because this B2 is simply connected. So note that pi 1 of S1 based at B naught is isomorphic to Z, and since B2 is simply connected and the fundamental group of B2 based at B naught is just isomorphic to the trivial group. So this shows that this I star is actually an injective map from Z, which is an infinite group, to the trivial group 0, which is a finite group, and which is not the case because there is no such injection. So this gives a contradiction, since there is no injective map from Z into 0. Hence, S1 is not a retract of B2. Similarly, one can prove there is no retract of the closed interval AB onto its boundary because we just proved there is no retract of B2 onto its boundary, where this S1 is just the boundary of B2, and we write this delta B2 to denote the boundary of a surface. So this is left as an exercise. Show that there is no retract of the closed interval 0 1 onto the set 0 1. This is simply connected, and this set is just the boundary of this set. So this proves our result.